Having covered the scientific basis for the anaerobic speed reserve, this video will focus on the practical side of the anaerobic speed reserve, the maximal aerobic speed and maximal sprinting speed. We'll see examples of how they can help coaches and athletes tailor training to enhance performance. One major but not exclusive mechanism underpinning the diversity of locomotive profiles seen in individual and team sports is muscle fiber type. Fast-twitch fibers are known to produce ATP at high rates, but at low capacity, resulting in premature neural fatigue. Recently, research using a non-invasive muscle scanner as a proxy of muscle fiber type showed that speed-dominant recreational athletes had a greater drop in knee extension peak power and took longer to return to peak power from baseline, up to 5 hours post-fatiguing Wingate exercises, compared with the endurance-dominant athletes whose knee extension power returned to baseline after 20 minutes. In a longer-term overreaching study using the same non-invasive technique, it was found that endurance-dominant athletes were able to better cope with high training volumes, achieving superior performance adaptations compared with speed-dominant athletes who displayed delayed recovery and were at higher risk of overreaching. Together, these studies revealed differences in both short and long-term training effects on athletes across locomotor profiles. By considering the underpinning differences across these varying locomotive profiles, coaches and practitioners may select more individualized training sessions to optimize training enjoyment and adaptive outcomes, whilst minimizing risk of all symptoms associated with forcing a square peg into a round hole. An athlete's locomotor profile reflects their individual propensity for dominance in speed versus endurance aptitude. Several studies in elite athletes reveal diversity of locomotor profiles exist within the same groups of individual or team sport athletes. Therefore, when beginning a training plan, locomotor profiling is recommended to calibrate the training approach relative to each individual athlete profile. This concept may be one of the strongest applications of the locomotor profile in sport. Typically, the training model employed is the same for all athletes within a group. It is only at a micro, day-to-day level where coaches more commonly individualize the specific training for a speed versus endurance athlete profile. The locomotor profile may help to better guide a coach in choosing an appropriate training model for their athlete. As shown in the figure, endurance profiles may be best suited to continuous, high-volume-based programs, including long HIIT. Conversely, giving a speed athlete profile such a program leads to risk of maladaptation or overreaching. After general training model selection, there are numerous day-to-day decisions that coaches make around training intensity, duration, frequency, and load, i.e. how much and how often. Given the variability in adaptation across athlete profiles, a framework is suggested for targeting aerobic development across diverse locomotive profiles. Since sprint training methodology does not include extensive slow and continuous exercise, speed athlete profiles in transition to sports with concurrent aerobic demands may be less familiar or experience discomfort early on with this modality. Even during low-intensity exercise, fast-twitch dominant athletes with speed profiles, particularly if glycogen depleted, as in they're under-recovered, or it may be their second training session of the day, may place increased reliance on fast-twitch fiber motor units, which, under a continuous low exercise intensity stimulus, can increase the VO2 slow component, making steady-state exercise unattainable. The increased dependence on anaerobic metabolism to meet the energetic requirements for the speed profile, in addition to the increased neuromuscular loading with longer high-intensity work, can create unwanted fatigue in the unfamiliar athlete, lowering the quality of subsequent repetitions and potentially future training sessions. For the speed profile athlete to develop aerobic adaptations and fatigue resistance, they need to recruit and adapt fast twitch muscle. This is also mechanically, physiologically, psychologically appropriate for the speed profile until the time at which a foundation of the aerobic stimulus and gait motor patterns are advanced. Consequently, using short intervals and repeat sprint training is likely a more appropriate approach in this population, and contrasts with the potentially more well-known long interval prescription that involves efforts around maximal aerobic speed of 2 to 5 minutes with 2 to 3 minutes of passive recovery. For example, short work intervals of 10-15 seconds, 20 to 30 seconds rest, running at around 120% of MAS at 5 to 10% of anaerobic speed reserve. This enables substantial exercise time at an intensity near VO2 max, whilst keeping lactate accumulation low. There are 4 aspects to justify repeated sprint training for aerobic development in speed profile athletes. 1, they tolerate these efforts well as they possess a greater proportion of fast-twitch fibers which contain higher baseline buffering muscle carnosine and more fast-twitch enzymes that have larger glycolytic capability. 2, they have lower cardiorespiratory fitness levels compared with the endurance-based profile, therefore relying more frequently on anaerobic metabolism. So producing lactate during training is not that different, and they just preferentially use their anaerobic system more. 3, there is an inverse relationship between fiber type, cross-sectional area, which is larger in the speed profile athletes, and fiber, VO2 max, largely explained by the matching of muscle fiber oxygen demand and supply. Time of VO2 max is inversely related to VO2 max during repeat sprint training. Therefore, in individuals with a lower VO2 max, it's better to use a suboptimal format in relation to time accumulated at VO2 max. That is well tolerated rather than an optimal prescription for time at VO2 max that is not well tolerated by the athlete. 4, there may be some peripheral acute responses linked to greater deoxygenation levels that can improve aerobic function at the muscle level, independently of the actual time at VO2 max of the session. This makes repeated sprint training a well-tolerated format for speed-based profiles, as their underpinning physiology suggests a greater tolerance to sustained high-intensity work in the anaerobic speed reserve domain. Therefore, these underlying profile characteristics may have important implications for training prescription. For low-intensity exercise denoted as intensity that is below critical speed, there are other models better suited to performance estimation and exercise prescription. Despite the evidence showing anaerobic speed reserve as a better tool for estimating time to exhaustion at workloads within the anaerobic speed reserve domain in individual and team sports, studies currently showing the efficacy of prescribed training interventions as a proportion of anaerobic speed reserves are limited. Many studies still prescribe interventions using percentages of maximal aerobic speed, which do not account for differences in an athlete's anaerobic speed reserve. For example, in rugby and middle distance runners, reported lower intersubject variability of change in blood lactate concentrations and time to exhaustion using percentage of anaerobic speed reserve compared with percentage of maximal aerobic speed. In addition, there is less variability in the acute heart rate response during high-intensity interval training when prescribed using the speed reach at the end of the 30-15 intermittent fitness test, which accounts for some anaerobic neuromuscular contribution versus maximal aerobic speed. Therefore, training prescription as a proportion of the anaerobic speed reserve is an important future research direction needed to determine whether individualizing high-intensity interval training by accounting for anaerobic speed reserve differences leads to a more uniform physiological stress and subsequent adaptation across diverse athlete profiles on a longitudinal basis. Surge moments within sporting events are commonly cited as differentiating medal outcomes in middle and long distance running, speed skating, and professional cycling. At the fundamental level, an individual must possess large enough maximal sprinting speed and maximal aerobic speed to be competitive within a homogeneous elite competition field, such as in an Olympic final. Without acquiring a minimum locomotive profile level, emerging evidence suggests performance may be compromised in certain types of races. Varying locomotive profiles can be found across team sport players, which can firstly directly impact the relative fatigue development between players during their high-speed locomotive performance during matches, and in turn logically predispose players to certain playing positions in the team that fits within tactical models. Naturally, improving both components of the profiles can enhance an athlete's tolerance to repeated high-speed sequences and may add a protective effect across dense periods of match play from an injury perspective. Importantly, however, any given repeated high-speed sequence is dictated, for the most part, by the tactical and strategic requirements of the match. This means that improving physical capacities may affect the relative fatigue development compared with a player's absolute running performance per se. From an organizational standpoint, conditioning coaches may seek to group athletes by locomotive profile rather than by play position only, especially when two athletes with divergent profiles may play the same position. Better understanding of these player profiles and the physical limitations that exist may offer important information for coaches aiming to execute a particular playing style. In conclusion, many individual and team sports have event demands that meet or exceed an individual's maximal aerobic speed or power. In order to develop the qualities needed to tolerate repeated muscle contractions at these high speeds or power outputs, it is recommended to use locomotive profiling as a framework to guide training content. This framework can assist in understanding athlete profile variability, selection of an appropriate training model, selection of an appropriate training format, and between workout recovery timeline guidance. From a performance perspective, by maximizing the training adaptations of both locomotive components, it can be ensured that we are meeting event performance demands. In the absence of valid and reliable measures of anaerobic metabolism, anaerobic speed reserve estimates provide many opportunities for the coaching and exercise science community to evolve their understanding of athlete locomotive profile development and how it fits into solving the performance puzzle.